When you look at a fighter jet tearing through the sky at Mach 2, it looks like the absolute peak of human engineering. It's loud, it's violent, and it literally defies gravity. So, you'd assume its engine is the hardest thing on Earth to build, right? Well, you'd be wrong. In the aerospace world, designing the engine for a standard commercial airliner is actually a much bigger nightmare than building one for a fighter jet. Today, we are stripping down jet engines to the bare physics to understand why commercial aviation engineering is the ultimate boss fight of modern manufacturing. Before we look at why they're different, we need to look at how they're the same. At their core, every jet engine is just a masterclass in Newton's third law of motion: action and reaction. Blast air out the back at extreme speeds, and the engine pushes the plane forward. If you tear any jet engine apart, the whole process boils down to just 4 steps: suck, squeeze, bang, and blow. First, suck. That massive fan at the front spins furiously, gulping down hundreds of pounds of air every single second. Second, squeeze. That air is forced into a series of compressor blades. As the blades get smaller, they compress the air by 20 to 50 times its normal pressure. This spikes the temperature by hundreds of degrees. Think of it as hyperpacking the oxygen so it burns like crazy. Third, bang. This super compressed air hits the combustion chamber. Fuel is sprayed, sparks fly, and temperatures instantly skyrocket past 2,700 degrees Fahrenheit. Fun fact, that is actually hotter than the melting point of the metal the engine is made of. Finally, blow. This blazing hot, high-pressure gas rushes backward. Before it exits, it spins a turbine at the back, which is connected by a shaft to power the fan at the front. The whole system powers itself in a continuous loop, thousands of times a second, blasting out the exhaust to push a 300-ton aircraft into the sky. So, if the physics are exactly the same, why is a commercial engine so much harder to design? It all comes down to one crucial industry term: bypass ratio. When an engine sucks in air, that air splits into 2 paths. The core air goes straight into the burner to eat fuel. The bypass air skips the fire altogether and just gets pushed around the outside of the engine by the big fan. The ratio of air going around the engine versus through the core is your bypass ratio. Let's look at a fighter jet. Fighter jets have a bypass ratio of less than 1. Almost all the air goes straight through the core. The engines are long and skinny to minimize drag. They are built for raw, explosive power. They have afterburners that dump raw fuel into the exhaust for a massive, fiery boost to go supersonic. Because performance is everything, the military doesn't care about fuel efficiency. And these engines only need to last a few thousand hours before they are ripped out and rebuilt. Now, enter the commercial airliner. Commercial engines have a bypass ratio of 10 or higher. That giant fan at the front generates over 80% of the plane's thrust using cold bypass air, barely touching the fuel. And this is where the engineering gets borderline impossible. Commercial engineers have to design under constraints that military engineers never have to face. First, insane lifespans. While a fighter jet engine tops out at a couple thousand hours, a commercial engine is expected to run flawlessly for 30,000 to 60,000 hours. That's like driving your car for over a decade straight at 80 miles an hour without ever turning the key off. Second, extreme safety. If a fighter jet engine fails, the pilot hits the eject button. If a commercial airliner carrying 300 people loses an engine over the Atlantic, it's a catastrophe. The FAA demands an in-flight shutdown rate of less than 1 in a million hours. Every single bolt, fan blade, and sensor must be absolutely flawless. Third, brutal economics. Airlines fly 12 to 15 hours a day. If an engine's fuel efficiency drops by just 1%, it can cost an airline millions of dollars a year per plane. Trying to make an engine that is massively efficient, unbelievably safe, and capable of surviving extreme temperatures for decades is a whole different level of difficult. To top it off, they have to pass the most brutal certification tests on Earth. Engineers literally fire dead birds out of a cannon into the spinning blades, blast millions of gallons of water and ice into the intake, and intentionally blow up fan blades inside the engine to make sure the casing can contain the explosion. Developing just one of these engines takes over a decade and costs billions of dollars. So, next time you're sitting in coach, drinking a ginger ale at 35,000 feet, take a look out the window. That massive engine humming beside you isn't just a piece of machinery. It is quite literally the absolute crown jewel of modern human manufacturing. If you learned something new today, hit that like button, subscribe for more breakdowns, and drop a comment below. Would you ever want to be an aerospace engineer? Thanks for watching, and see you in the next one.